In this video, we're going to take a look at circles. So we've been reviewing the coordinate plane and some different things we can do with the coordinate plane. We can plot the coordinates or ordered pairs contained within a relation, and we can speed up graphing using symmetry and intercepts. And then we talked about how to find distance between two coordinates on the coordinate plane using the distance formula, and then how to find the midpoint, or the point located on a line segment connecting 2 points on the coordinate plane. So today we're going to look at circles, which is a very specific relation. It was a relation in which all the coordinates, when plotted, would form a circle on the coordinate plane. So that's what we're going to start with is the geometric definition of a circle. So geometrically, a circle is the set of all points in the plane that are equidistant, or the same distance, from a fixed point called the center. So if you have a circle, so you've got a circle, the circle will have some fixed point called the center. Now the center is not part of the circle, but it's needed to create the circle. And then you've got this fixed distance that all of these points, so any other point you pick that is on the circle, these points are all exactly the same distance from this point called the center. So this is the center, and then this distance from the center to any point on the circle we call the radius. And radius, we usually just use lowercase r to represent radius, that length. So all of these points right here, any point you pick, there's an infinite number of them. They make up the circle, and then the center and the radius are just important components of the circle, but the circle itself is all these points here. That's the geometric definition. So what if we want an algebraic definition? What if we want a definition involving the coordinate plane with x's and y's and ordered pairs and the like? So we need to be the same distance from some fixed point called the center. So let's say we're on the coordinate plane. I'll just do the first quadrant here. Doesn't really matter where we're at. So let's say this is our center. We're going to give the center a coordinate. So let's say we're at HK. So I'm going to call the first coordinate H and the second coordinate K. And then that's the center of some circle. So let's say this is our circle here. So all of these points are the same distance away. We'll call that distance R for radius. Now I know mine's not a perfectly drawn circle, but you get the idea. So that makes all of these coordinates right here, those are coordinates on the circle. So we're going to have x, y represent a generic point that is on the circle, and hk be the specific point that is the center, and r will represent the specific distance for the radius for that circle. So we're just going to use the geometric definition, and come up with an algebraic definition. So we know that all of these points x, y have to be the same distance away from this point, the center. So the distance between any point on the circle and the center would be given by our distance formula. But that distance has a name. We've called it r. We've called it r. So if we square both sides just to remove the radical, so we don't have to write the radical, we get the common representation of a circle on the coordinate plane. So that's our algebraic definition for a circle. So it doesn't rely on geometry, it just relies on the coordinate plane. You just need to know the center and the length of the radius. You can dump it in and you get an equation or a relation for all the points on that particular circle. So our algebraic definition is we're going to let HK be the center, and we're going to let R be the radius, then the standard form of an equation for an equation of a circle is given by what we just came up with, x minus h squared plus y minus k squared equals the radius squared. Now, what if your circle is centered at the origin? Well, then h and k would both be 0, and you would just get and then as you'll see in mathematics, we often use what's called a unit circle. So the unit circle refers to a circle whose center is the origin and whose radius is length 1. So the unit circle would be a center of 0, 0, and a radius of 1. That's where unit comes from, as the radius is 1 unit in length. So that would just be x squared plus y squared. Well, 1 squared, if the radius is 1, 1 squared is 1. So those are two special cases of a circle. So if you have a circle centered at the origin, it's just x squared plus y squared is the radius squared. If you have the unit circle, it's centered at the origin and has a radius of 1. So for example, let's say we wanted to write the equation of a circle whose center is negative 8, 4/11 and has a radius of length 8. So h would be negative 8, k would be 4/11, and r would be 8. So we'd have x minus negative 8 squared plus y minus 4/11 squared equals 8 squared. So that would simplify to x plus 8 squared, y minus 4/11 squared equals 64. We'd have an equation for that particular circle. So what if you needed to graph one? Well, as long as it was written in standard form, graphing is pretty straightforward. So I can look at this and say, oh, wait, that's just x minus negative 3 squared, and that's y minus 2 squared equals 16. So then I have 16 is just 4 squared. So h is negative 3, k is 2, and r is 4. So x minus h, this is h, and then y minus k, that's k, and then it should be the radius squared. So that's what's being squared is 4. So now I can come over here and graph that pretty quickly. So hk, so I go negative 3, 2, there's the center. The radius is 4, so I can go 4 in this direction, 4 in this direction, 4 in this direction, and 4 in this direction. Now I should be able to go 4 in any direction, but it's easiest to count up, down, left, and right, and then just kind of freehand the circle from there. So no one would expect it to be perfect. So you would just do the best job you can drawing your circle. Just do the best job you can drawing a circle through those 4 points. So as long as you're in standard form, it's pretty straightforward. Now there's another form called general form of a circle. And general form is used for various reasons. We'll go more into this when we study our conic sections later. But standard form is essentially when you multiply this all out and move everything to the left hand side. So let's see what would happen if we did that. So if I was to square this, and then square the one with y in it, now remember h and k are constants and r is a constant. X and y are the only variables. X and y are the only variables. So if I use the commutative property, and I subtract r squared from both sides, I can end up here. So this right here is a constant. This right here is a constant. And this right here is a constant. Those are all constants. Only x and y are variables. So whatever h is, whatever k is, and whatever r is, those are fixed. They're just regular old everyday numbers that don't change for any given circle. So since those are constants, I can just rename them as some specific constant. So I could say, for example, I could say negative 2h is, I'm just going to call that a, and negative 2k, I'm just going to call that b, and k squared minus r squared, I'm just going to call that c. And we get what's called general form of a circle. So everything's just on the left-hand side and it equals 0. So we have an x squared, a y squared, an x, a y, and a c. Well, the c is a constant, a is a constant, and b is a constant. So occasionally we'll run across general form, and in general form, it's not obvious what the center is. It's not obvious what the radius length is. So if you come across general form, it's not as easy to graph it. So here's general form here, x squared plus y squared plus 6x minus 4y minus 3 equals 0. So this is general form. So it's not obvious to us, it's not clear to us what h, k, and r are. So let's see if we can't figure out what the center and radius are. So let's go ahead and rearrange it, use the commutative property, and put the x's next to each other, the y's next to each other, and let's put the constant on the other, the one that doesn't have a variable, let's put it on the other side. Then what we can do is complete the square. So we can complete the square for x and complete the square for y. So what I want to do is I want to create a polynomial here that's a perfect square trinomial. So to do that, I divide 6 by 2, which gets me 3, and then I square it to get 9. So I do 6 divided by 2, I square it, and it gives me 9. So then what I'm going to do is I'm going to put a plus 9 here. So I added 9 to the left side of the equation. And so to balance things out, I have to add 9 to the other side of the equation. So that keeps everything equal. The left side and the right side are still equal. Now, for the y's, I'm going to do the same thing. I'm going to do negative 4 divided by 2 and square it. I'm going to get it 4. So I'm going to do a plus 4. But I just added 4 to the left side of the equal sign, so I need to add 4 to the right. I need to keep things balanced. So this is now a perfect square trinomial. It factors into x plus 3 times x plus 3. This is a perfect square trinomial. Y minus 2, y minus 2. And the right side is just 16. So I get x plus 3 squared, y minus 2 squared equals 4 squared. Now we can get h, k, and r. So h is negative 3, k is 2, and r is 4. But you might recognize this. We graphed this earlier. This is the equation that we just graphed previously. So we graphed this earlier. Now I did that on purpose. I wanted to show you that if we had general form or a form that wasn't standard form, we could make it look like standard form and then graph it from there. So there's our x coordinate for the center, there's the y coordinate for the center, and there's the radius. Negative 3, 2, and 4, which we graphed that earlier, where negative 3 up 2 was our center, and then we went 4 up, 4 to the right, 4 down, and 4 to the left. So we graphed that one earlier. We don't need to graph this one again. So h negative 3, k was 2, r was 4, and we graphed that one earlier.